Welcome to today's class on functional analysis. Today we discuss Hand-Banach extension theorem. So for proving Hand-Banach extension theorem, we require a supporting lemma. So we prove that lemma first. So lemma. Let X be a normed space over K. F belongs to X dual and F not equal to 0. Let A belongs to X with F of A equal to 1 and R positive. Then UAR intersection 0 space of F is empty if and only if norm of F is less than or equal to 1 by R. So we prove this proof. Let UAR intersection 0 space of F is equal to 5. Let UAR intersection Z of F is empty. Now if X belongs to X and F of X is not 0, then A minus X by F of X belongs to 0 space of F. This is because since F of A minus X by F of X, this is equal to F of A minus F of X by F of X, since F is linear. So this is F of A minus 1, and you know F of A is 1, so 1 minus 1, it is a 0. Therefore, A minus X by F of X belongs to 0 space of F. And since UAR intersection 0 space of F is empty and A minus X by F of X belongs to 0 space of F, implies A minus X by F of X does not belong to UAR. That is, therefore, norm of A minus X by F of X is greater than or equal to R, because A minus X by F of X does not belongs to AR implies distance between A and A minus X by F of X is greater than or equal to R. So this implies norm of X by F of X is greater than or equal to R. So this implies norm X by modulus of F of X is greater than or equal to R. So this implies norm X is greater than or equal to R times modulus of F of X, or from that you will get, so this implies modulus of F of X is less than or equal to 1 by R times norm X. Now we have, so by definition of norm F is equal to supremum modulus of F of X such that norm X less than or equal to 1. So this is supremum So this is less than or equal to supremum mod norm of x by r such that norm x less than or equal to 1. So this quantity is less than or equal to 1 by r. Therefore, norm f is less than or equal to 1 by r. So we have one part. So for the converse part, conversely suppose that norm of f is less than or equal to 1 by r. Now if we are going to prove that UAR intersection set of f is empty. So if x belongs to UAR, that is norm of x minus a is less than r, then modulus of f of x minus 1, that is equal to modulus of f of x minus f of a, because f of a is 1, that is equal to modulus of f of x minus a, and by definition this is less than or equal to norm f into norm x minus a. So this is equal, and norm f is less than 1 by r. So this is norm f is less than or equal to 1 by r. So this is less than or equal to 1 by r into norm x minus a, and you know norm x minus a is less than r. So this is less than 1 by r into r, that is modulus of f of x minus 1 is less than 1. So that f of x is not equal to 0. Therefore, x does not belongs to. So our choice is x is in UAR, then x does not belongs to 0 space of f. Therefore, UAR intersection 0 space of f is empty. So this proves the lemma. So now we prove Hahn-Banach extension theorem. So we state the theorem. Let x be a normed space over K. Y be a subspace of X. And G belongs to Y dual. Then there is a sum F in X dual such that F restricted to Y is G and norm of F equal to norm of G. So this is the famous Hahn-Banach extension theorem. So for a subspace Y of a normed space X and G in Y dual, this theorem guarantees that there exists at least one Hahn-Banach extension of G to X. Now we prove this theorem. Proof. If G equal to 0 on Y, then we can let F equal to 0 on X. So this proves the case of G equal to 0. Now assume that G is not identically 0 on Y. Let A belongs to Y be such that G of A equal to 1. Now let R equal to 1 by norm G in the previous lemma. That is, R equal to 1 by norm G implies norm G is equal to 1 by R. So we can apply the previous lemma. Therefore, by previous lemma, U Y A 1 by norm G intersection 0 space of G is empty. Let E equal to U X A 1 by norm G. So this is U by A 1 by norm G is an open ball in Y with the center A and radius 1 by norm G, and you consider the same ball as an open ball in X. Then E is a non-empty convex subset. Non-empty convex subset of X. And is disjoint from, and E is disjoint from zero space of G. So we have set of G is a subspace of X. Therefore, we can apply 7.3. This here E is a non-empty convex subset and set of G is a subspace of X such that E intersection set of G is empty. That is, E is a non-empty convex subset of X and set of G is a subspace of X such that E intersection set of G is empty. Therefore, we have all the requirements for applying theorem 7.3. Therefore, by 7.3, we have there is some f in x12 such that f of y equal to 0 for every y in 0 space of G, but a real part of f of x is not equal to 0 for all x in E. Which implies f of x not equal to 0 for all x in E. Now we have A belongs to E, therefore f of A not equal to 0. So replacing f by f of A, we have f of A equal to 1. So this is because our new f is f by f of A nu f. So this is just a notation, nu f. So that implies nu f of a is f of a by f of a. So that is 1. So if we replace f by f of a, we have f of a equal 1. Now f restricted to y is from y to k, and 0 space of g is contained in 0 space of f restricted to y, and g of a equal to 1, that is equal to f restricted to y of a, because f of a is always 1, so f restricted to y of a is 1, and our choice of a is in y such that g of a equal to 1. Now you let y belongs to y, then y minus g of y into a belongs to 0 space of g. This is because g of y minus g of y into a, this is equal to g of y minus g of y into a. Now again, by linearity property of g of y minus g of y, you can take this g of y outside into g of a, and this is g of y minus g of y into 1. So this is equal to 0. So y minus g of y into a belongs to 0 space of g. And we have 0 space of g is contained in 0 space of f restricted to y. Therefore, y minus g of y into a, this belongs to 0 space of g, that is contained in 0 space of f restricted to y. Now y minus g of y into a belongs to 0 space of f restricted to y implies f of y minus g of y into a, this is equal to 0. So this implies, since f is linear, this is for y in y. So this implies f of y minus g of y into f of a, that is equal to 0. And you know f of a is 1. So this implies f of y minus g of y equal to 0 for y in y. That is f of y equal to g of y for y in y, or this implies, the meaning of this is f restricted to y is g on y. Therefore, norm g is equal to norm f restricted to y. This is less than or equal to norm f by the definition of norm. We take this as equation 1. On the other hand, we have E intersection set of G is empty. This implies E intersection set of F equal to 5. Since E is contained in Y, which is contained in X, and F equal to G on Y. That is Ux A 1 by norm G intersection 0 space of F is empty. Therefore, by previous lemma, norm f is less than or equal to 1 by r there. So here r is 1 by norm g. So 1 by norm g. So this is norm g. That is norm f is less than or equal to norm g. This is 2. So I already have 1. Norm g less than or equal to norm f, and here norm f less than or equal to norm g. Therefore, from 1 and 2, norm f equal to norm g. So we have f is an extension of g and norm f equal to norm g. This proves Han-Banach extension theorem. That's all for the day.